Okay, cool. So here we are to have Vinh summarise his PhD for us. Second PhD submitted in the last month. Probably the last one for a while. I can't see any other PhDs getting submitted for a bit. So enjoy this while you can, as we've just been discussing. Morning tea on Friday. I'd like to welcome all these unfamiliar faces. Every single person here I'm going to have a meeting with today, but anyway, never mind. Good. So yes, this is basically what I think this is trying to achieve, and it'd be good if everyone gets to do this, is just put the whole PhD thesis together as a summary in context, so everyone at least knows what Vinh has done, and this is his last presentation in the school. And he's going to go back to Vietnam. We're never going to see him again, so be sad. All right.
Okay, thank you everybody for coming today, especially for our team. It's my pleasure to come here 4 years ago and start my PhD. I want to say many thanks to all of you and all of your support and encouragement for the last 4 years. And this is some summary about my work for the last 4 years. So I have given the name is Dynamically configurable architecture for multi-GNSS receiver. So that is an outline for today. Of course, that sometimes everything starts from problem and motivation. And after that, it is my analysis on the feasible architecture that can be applied for multi-GNSS receiver. And after that, it is to some proposed architecture that is can be applied for multi-GNSS receiver. And the last thing is some work is very much more related to signal processing about the effect of sampling frequency, and so the solution of this. So there is, I think, it's much familiar with all of us now, because instead of only GPS, now we have like 3 more global navigation satellite systems like Galileo from Europe, Vinh from China, and Luna from Russia. But not only global navigation satellite system, we also have a regional navigation satellite system like the QZS from Japan and the IINS from India. So what happened? It means that now more satellite. There is the availability map for the satellite. So we can see that Australia is one of the areas that have the highest coverage of satellite. Yeah, so we have a lot of benefit on this. Not only that, now we have like more satellite. Of course, more satellites mean that at every time you can see that now, instead of only like 4 or 5 satellites, you can have like 10, 12, or maybe 15 satellites at one time. And the second thing is that now, if we can integrate all of these satellites together, we can improve the accuracy and increase the integrity. Yep, that is some motivation for this. The first thing is that for the urban canyon. Yeah, so in urban canyon, when you drive through the urban canyon, sometimes you see that, when, for example, when I drive through the like CBD, instead of showing on your navigation, like TomTom navigation, that you are driving on like in George Street, it will show you driving in like Flinders Street or maybe Elizabeth Street. So the problem here is that it's because of the urban canyon that is block the signal. But instead of receiving the live size signal, you will receive like some reflex signal. So that's why the navigation, the receiver will show you the wrong position instead of the right one. So if you have more satellite now, so you can receive more live size signal. The second thing now is that, of course, is for the surveying, that's precise positioning. You can improve this. And also for aviation and for agriculture. So with aviation, you can improve the accuracy for the auto landing system, or you can improve that like the self-driving tracker, and also self-drive car. Yeah, but there's also always a challenge. There is the mobile revolution. You can see that it's from a very like a bridge, getting smaller. And now, and large again. So that is the benefit here, that the small thing that this can help you to reduce the size. But because it's integrated too many chance states at one chip, so the power consumption will become the problem. And now for the important like the smartphone with the big LCD screen, it's going to consume a huge power. So battery will become the trouble. That is the trouble of the battery. So performance versus battery life. So it also affects for GNSS receiver the same thing. With a single chip receiver, you can have like a more battery, but now if you want to integrate more receiver inside one, it requires a high power consumption. So start from these challenges, I try to clarify some physical architecture that we can apply for multi-GNSS receiver. And here I separated like two big categories. The first one is software receiver, and the second one is hardware receiver. It is the first thing that someone did some clarify like this. So for software receiver, we have like from full software receiver. This means you only need the receiver is connect directly to the PC, and everything you process on the PC is software receiver. The second one is using the GPU. This means that using the graphical processing unit to process the signal. That is for the software. And also for hardware, we have like four more types here. The first one is the embedded single core processor. The multi-core processor is mean here that you have a board, and this process instead of using the PC, now it is like an MCU or a chip inside a board. This is process like a receiver. And the last one here is that now as we try to integrate everything inside one chip. It's from like a single core to the multiple core. So what's the problem here that we have too many. But how can we evaluate this? The feasible architecture, and which one is the most suitable for multi-GNSS receiver? So with this demand, I propose like a cost function that can be evaluated all of this architecture based on 6 characteristics. The first one is delivery cost. It means that how much money, how much like manpower you need to give to process to develop like a receiver. And opposite with this is the non-programmability. It means that how can you reuse all of your resources. Like for example, like a software design, you can reuse all of you can design like a class or like a method, you can reuse this when you want to combine, make a new one. But for hardware receiver, you can't do the same thing. The other thing here is that the power consumption and the resource utilization. Of course, more resource utilization is also more power consumption. Yeah, and vice versa. And the last thing is that the I/O latency and the memory capacity requirement. So the important thing here is that when you receive the signal signals go straight from the front end. So if you have the I/O latency is very high, then in this case you need like a memory to store the data before you can process it. But if you can process it like immediately, so you don't need the memory to store the data before you process. So this is 6 characteristics I propose to evaluate the physical. So in this case, I try to normalize all of these character and draw it in this by the web. So you can see here is that all of this existing architecture, none of them can provide that the minimum requirements that's for the multi-GNSS receiver. So from this, I propose like 2 more architecture. Is in the best manual, I think is much more suitable for multi-GNSS receiver. So the first thing is I call it like fully programmable custom core. So it means that now instead of have everything like usually for the design you have like the correlator is inside an FPGA, and after that the tracking and acquisition this can be like PC or it can be like an MCU. So I try to put all of this now in one chip and design this core with this dedicated instruction set. It's only for GNSS receiver. And this is the the memory map, and also the some instructions and quantities. And after propose this, I also apply the cost function to evaluate, and you can see that okay, in this case now, it can reduce this. Yeah, but it's still not the most minimum one I need, because the problem here is that that is the constraint of the processing speed for the custom core. In that I design only like 16 bit for the data part, so it only can process like 16 data sample at the same time, and after that I have to repeat the routine again. So because of this constraint, so it's only suitable for to do the correlation. If we also want to do acquisition and tracking inside this custom core, is only can provide for like GPS L1 CA. But if you want also use this for L1, L5 or E1, it's not suitable. So the problem here is that it only comes from the correlator. Because the correlation you have to keep its real time, and every time when you receive one sample, you have to continue and you have to keep processing it. So I propose the other architecture here is that instead of this, now I propose a new dedicated pipeline correlator, and it's connected to the core controller, and also it has the chain encounter and the graph selector to process this. So in this case now, I'm start from the idea here with that. Because for all the GNSS signal, you can see that the required IF sampling frequency is usually very low, like 4 megahertz, and max only like for E5 is like 100 megahertz. But it's still much lower than the processing performance of the FPGA. So instead of using like doing like in serial here, I'm thinking is that okay, why do we multiplex this? So it means that in one hardware, you multiplex to process like multiple channels. Yeah, because the processing speed requirement here is very low. So to do this, I propose like a programmable pipeline baseband circuit. It's still to do this, the same thing. But now, because of the lower processing speed and inherit the advantages of RAM-based register over the register-based register here, with this architecture, I can directly programmable and multiplex process is like 16 GPS L1 CA channel in one resource. In resource for only one channel, 8 Baidu, 4 Galido, and 1 GPS L1 channel here for only one, in only one design. Yep. So in this case, you can see that the resource utilization is significantly reduced here if we compare with the conventional one, and also with the fully programmable custom core. So in this case, it's only consume like 5.2% of resource utilization, and also the power consumption is also reduced. Yeah, this is the compare for the power consumption. So in all case here, when I configure this architecture to process, it's only have the smallest of power consumption, and at least it can reduce like nearly 50% of power consumption. Yeah, and finally, when I apply the cost function to evaluate, so the last one, the pipeline correlator programmable architecture, is have the minimize for the cost function, or is needed one here. This the probable architecture is have the lowest cost function. So the other thing here you can see that also from the modern signal characteristic is that the sampling frequency is usually a bit like 4 times higher than the GPU rate. So if you, after we can wire off all the carrier, so we don't need to process at very high speed. Because if we increase the speed, also it's increase the power consumption. If we can reduce the processing speed, we can reduce the power consumption. So start from this idea and think, okay, now because the sampling frequency is too high, if we can decimate or downsample the the sampling frequency after we down convert the IF signal to baseband. So we can reduce the power consumption. So, but it's always have a problem with the decimation here. It's that when we decimate any signal, we need like an anti-aliasing filter. Otherwise, we have the aliasing from the high pass signal here. So usually for all the other decimation filter, they usually use a very complicated filter to keep the to remove the aliasing. But here that is start from, I'm thinking that because when I try to draw the frequency response of the moving average filter, for example here like 4 times. So if I give the moving average like 4 times of moving average filter, this is the frequency response of this. And also the correlation is also working like a second filter, because you need, this is the matched filter when you try to match the local code with the incoming signal. So it's also like a second filter here. So instead of like only filter the signal here, the anti-aliasing filter here is when we working at like filter of a power signal. So this is the power spectral density of the spreading code signal. So after we apply the filter, you can see that, yeah, of course, we lost some signal, but the shape is still the same. And the most important here is that the main lobe here is still keep the same, but also we can reduce the side lobe. So that's very good for tracking the BPSK signal. Yep. So this is the conventional, they call this the recursive MTAP, MAV, the moving average decimator architecture. Is that if you want to have like an MTAP, you need like at least the MTAP and bit register. And after it's moving through this, we use the adding and the subtract to get the output signal. And every time after this, if you want to have the downsample rate, you need an ratio to get the frequency you want to downsample. But in this case here, it's very difficult to make it become very configurable, because every time you want to drill this, you have to enlarge or smaller the number of registers you need here. Yeah, and it's not suitable for make it become very configurable. So I propose a new MAV decimator here. So start from the idea here is that we always try to downsample is like a power of 2. So if you want to downsample it's like power of 2. If you want to downsample like alpha, so we need like n is equal to double of alpha for the decimator. And with this one now you can separate it to store is only in 2 registers. And using the latency signal to get the output signal here. It's like power of 2 times, power of 2, the power of 2 division of the input frequency, of the input density rate. And the other thing here it does, with this idea here, because they only have add and subtract. So if you have the output here is will be the output bit here is will be increase. But in my case, because it's only like a power of 2, so I only need to use the C module to make it become like exactly only n1 bit. So we don't need more bits, so we still can reduce the resource consumption. Yeah, and there is some comparison for this when we apply this idea here. So this is for the conventional. When we apply for a 16 bit L1 CA, 8 bit or 1 bit L5 channel. So it depends on the downsample rate. You can see that the higher downsample rate, the lower power consumption we need. And also in terms of signal to noise ratio, the output signal after correlation. So we usually have like minus 0.5 dB. So it's this is the loss of signal power of the signal to noise ratio. So it's still it is worthwhile to do this here in terms of if we want to save the power. Yep. And the last thing it does now, that is the same effect of the sampling frequency. That one is much more like a signal processing thing. But before, like when I read like through the literature, when they're talking about the sampling frequency, especially for BPSK signal, they think that okay, we always have like a triangle for the correlation when we have the auto-correlation of a broadcast signal. But it's only happen if the signal here is continuous, like when we have in this animation. But actually, we never have the continuous signal, because all the signal we have is the sample signal, and it's the discrete of discrete. So in this case, you can see here. So with the same input signal, but we can have like two different local generated signal, and the alignment here is different, but the correlation value, the autocorrelation value you have is still the same. So, because of this effect, the correlation now, instead of a triangle, it's become like a staircase. So with this staircase, you can see that instead of very sharp peak, now it's become a flat peak. And with this flat peak, it will affect to the derive discriminator function. That is lead to the zero feedback array here. So during all of this array, that the discrimination function doesn't work. It doesn't give you any changing. And for all the changing is smaller than this array, the derive discriminator function can't detect it. So we try to test it again with the live signal. So that is with the result with the live signal when we try to extract is when the sampling frequency here is 4 times of the chipping rate. So you can see that, yeah, this problem is appear clearly. But after that, when we try with only 1 kilohertz difference of the sampling frequency, is here is 4093 megahertz. All of this problem disappear. So why is happened? Yeah. So the problem here it is because of the effect of the ratio of code phase. So the ratio of code phase here is what it is. This one is start from the code ansio generator. Yeah, it's just usually when you want to generate like a local code, you need an ansio to generate the frequency. So we use the this is the code accumulator and this is the increment. So by changing the code increment, so we can changing the frequency, the output frequency. But because it's in digital domain, so after the code accumulator is overflowed, it will generate like 1 punch. But the remain value of this code accumulator is the ratio code phase. Or in terms of time, you can see it here. So this is the time difference between the start of a code chip, of the local generated code chip, with the first sample input of the incoming signal. The first code is this one, the second code, and for the third code, that's one. And so now with this we can see that is the effect of this. And we try to use some conventional result from like other expert research to measuring this problem. But when we try to do this, it is the derive tracking error when we try to apply the methods proposed by Best. I think that one is from the Best paper, and after that they apply it in the Kaplan book everywhere. People using this when they want to estimate the derive tracking error. But here now I try to draw it when we're changing the sampling frequency. That is not, yeah, with the step here is that like 0.1 sample per chip. But you can see that all the error is very small. Yeah, and the maximum is only like 3 meters here. But the real one when we have it that's much more than that. So I try to propose a new one. It can be much more accurate estimate this. And this is the one we have, with the proper one. You can see that now, instead of very small one, so when the sampling frequency is like an integral time or rational, of the chipping rate. So the error is significantly increased. Yeah. So one of the problem here is that because they haven't taken into account the effect of the ratio of code file. And yeah. Yep. So now it does try to find a solution if the sampling frequency is like an integer time. So after comparing all of this, we find out that okay, the problem is that is the ratio of code file and this distribution. Because it like when it's an integer time of sampling frequency, when the sampling frequency is integer time of the multiple code trace, so the ratio of code file is like a constant for each code chip, and that's why it leads to the significant error. So if we can now design or system one of these ratio of code file to distribute it uniformly inside the separate interval, so we think that maybe it can help to reduce the effect. So this is the solution for this down here. It is, for example, here you can see when the sampling frequency is 4 times of GPU rate, so all the ratio of code file is like constant. So now we try to zeta it. Yeah, by adding like a random value here. So but the problem for when you jittering here is that sometimes the code chip generate is not still only belong to this chip, it maybe belong to the next chip or belong to the previous chip. So we have to take into account this problem. Yeah. So and after we apply all of this, this is the efficacy of this solution. So after we apply all of this, you can see that all the distortion is look like totally average with 3 proposed solutions: the size zeta, the random zeta, and the soft zeta solution. So in this case, that you can see that the random zeta solution and the soft zeta is look like better than the size zeta. And this is the derive tracking errors when we apply on this solution. You can see that, yeah, instead of providing significant errors, now we can reduce significantly. Yep, and this is the theoretical solution. And now how can we apply this on the circuit? And to apply this on the circuit, so we are trying to add another layer. Instead of a normal code generator, we still do the same here. Now, we add another layer on top of this. Yeah, to generate the zeta value and also to select the code chip that we want to guess. Yeah, and the thing here is that because the code chip you need here is you only can have like the K chip and you can't have like the K chip and the K plus 1 chip at the same time. But you always can easily have the K chip and the K minus 1 chip at the same time and put it through a register. So this is the solution here is that now we try to zetaing, we only use the negative zeta instead of positive zeta. So in this case, it keep you can choose the code chip you want using only like zip register. Yeah. And this is the solution for the conventional architecture. But now this, if we want to apply for our proposed RAM-based architecture using the pipeline correlator, in this case we also propose the other one here is that the RAM-based design for this. So it is almost the same. But instead of register here, we replace all the register with the RAM-based design. Yeah. So in this case, you can see that when we're adding this directly to the conventional architecture, so the resource consumption increase very small, nearly like 300 slide here for the conventional architecture, and the power consumption also increase very small, only 2 watts, only 2 watts for this, 2 milliwatts, sorry, 2 milliwatts. But if we apply this for the pipeline, then you can see that we can also reduce the resource consumption and the power consumption for this. And there is some experiment result I want to show. So this is the DLL tracking errors when is the sampling frequency for time and interval time before we apply the Z3 solution. So you can see this like heartbeat. So this heartbeat is because of the flat peak. So that's during all of this, the DLL discriminator can give you the right result. But now after we apply, this is the solution. You can see that all the errors become very small and smooth. And this is the table which shows you the result for all of this. So this is the DLL tracking errors with the live signal. So without the digital, you can see that the error is can from like 16 to 22 meter, depend on the power signal we receive. But after we apply this, so you can reduce it significantly and compare with the one. The sampling frequency, the average is 4093, the one we can see that is very smooth before. So you can see that in some case our solution is better than when you apply the solution for the integral sampling frequency, is still better than the irrational sampling frequency here. And this is the last one is for the deviation of the variation of the position. So if we don't, when we have, without applying the jitter solution, you can see that the variation, the position is very high. And after we apply this, you can see that all of this position is much more precise. Yeah. And this can reduce the DIMS here is around like 4 times. Yep. And there is some future research direction. So the thing I haven't mentioned here is that the effect of the secondary code on the signal. So this is the other problem here. So we need to deal with this because for the modern signal, modern GNSS signal, we have a problem to deal with the acquisition of the secondary code. So one of the ways here is that instead of using FFT for the primary code, we're thinking that also can use the FFT acquisition for the secondary code. The second thing it does, nowadays that's with the development of like new FPGA chip and the system on chip, thus we have like an ARM Cortex inside an FPGA, and beside that we have a lot of very huge fabric FPGA. So we can thinking in the other way that now we try to implement like a system on chip receiver. Thus we need to combine our proposed architecture with a new interface and instruction for the ARM Cortex chip. And the third thing it does, now because we can decimate the baseband signal, so we can reduce the processing speed for the correlation. So instead of using like a serial correlation, the other thing is now, why don't we also multiplex the correlation to do it in parallel? So we can also reduce the resource consumption here. And the last one is about the effect of sampling frequency. So all of the effect of sampling frequency here, I just only investigate is for the tracking. Acquisition, I haven't mentioned. So it is something we need to deal with this. And before I had read some paper that they're talking about that it is the effect of the self-correlation phenomenon. But in this case, that's only thinking about the effect when it has the effect of the Doppler. But now we also need to have the effect of the sampling frequency. So that is will be much more big problem for the acquisition. We will also take into account the effect of sampling frequency, especially to reduce the time to first fit the signal. And the last one is that all of my investigation is only for BPSK signal. But how about the bulk signal? That is still a question. Yep, thanks. And that is all of the summary about my thesis. Thank you. Luckily, I have like several ones. Thanks.
Okay, questions? All right, I'm going to start some questions.
Yeah.
a bit late now, but anyway. Can you go back to your staircase, right, quite close to the beginning? Actually stop, go forward again. I'm looking at that error, that one on the right.
Yep.
That's actually wrong, isn't it? That plot. If you look at it on the right, it should be sort of downward sloping things, and then on the right-hand side, it should be upward sloping things.
No, this is when we compare this with the ideal one.
Yeah, yeah. And what I'm saying is,
Yep.
if on the left, if this blue line, right, is this blue line minus that, then it should be positive there and positive there, so it should come down to 0 and then up again, and then this one should come.
No, but this one, yes, it's below the line. And then this one is minus.
Yeah, look, 0, right? 0 is positive on the left-hand side and positive on the right-hand side. Right? That's positive and that's positive. So this should be positive and that should be positive.
Yeah.
So
Yeah.
that managed to get through you and me several times. Anyway. The other question I got is this one. So a couple of things. I can't remember. Did you actually plot the amount of jitter against the error? Because the jitter must be introducing some sort of error itself, right?
Yep, that's the error here is that we introduce it as, you can see that because we use a negative jitter, so it will be least less to the, all of the code it will be jitter like half of the jitter amplitude. But the good thing here is that after we put it through the DLL loop filter, it will be, it will filter all of this error and it will become good. It's just only effect for like first few milliseconds, but after few milliseconds, it will become very good.
Because when just looking at that, right, you would expect if you're comparing the very right hand column,
Yes.
to the 4.093, then I don't know, maybe that's supposed to be like ideal, right?
Yeah.
Because it doesn't have any of these staircase effects in it. Then it should always be better than the jitter, because the jitter itself has introduced some noise. Or is there actually still some of this effect that we're talking about still in the 4.093, and the jitter is removed completely from the left-hand side?
Yep.
Because you've got your columns there. Sometimes the 4092 is better. Sometimes the 4093 is better.
So I think it's the only here is that in most cases the 4093 is always better, but it's only in some case when the signal is strong, or maybe in this case that also combined with the effect of the Doppler, that is give the solution is better.
Okay, so they're listed in order of their CNO.
Yeah, it is in order of CNO and also is the Doppler.
Yeah, right.
Because the Doppler here also contribute to the zeta. So in some cases, give the zeta better result, and it lead to the worst result for the idea we have here.
Oh, you mean sometimes the Doppler helps you?
Yep. Sometimes the Doppler
Yeah,
have.
right.
Yep. And sometimes the Doppler have this
Yeah.
and this lead to this one.
Is this simulated or is this real data?
It's a real data.
So the 4.092 is from which receiver?
The Dwayne Blake IF,
Okay, and the 4.093 is from
the same.
same data, right?
I've got a question. One of the reasons why you get big benefit with your pipeline approach is you're kind of using the resources that are built into the FPGA, namely the memories.
Yep.
A lot of FPGAs now have internal math blocks, like hardware adders.
Yeah.
Did you end up using those, or?
Actually, I haven't enough to using all of this hardware and the block. So I develop all of this from like a very simple FPGA block.
And it's always Xilinx, right?
Yeah.
Yeah. But Xilinx have those as well, the
Yeah.
math blocks. So
Yeah.
they've got hardware adders and accumulators that
Yep.
are kind of meant to be used for DSP type things.
Yep.
So if you were using those, instead of just building it up with logic elements, it should
Yeah.
get even better, shouldn't it?
Yeah, I think so, but the problem here is that if you want to compare with the conventional one, so the easiest way is that we're using the logic element.
Yeah.
Because all the conventional design now they're using the logic element.
Yeah.
I think that's useful if you're talking about multi-bit, right? We're talking about 1-bit sampling or 2-bit sampling.
That's why it's multi-bit. It doesn't affect. Because as you can see that all of this is like at least like N1 input bit, so it can be changed.
So the big RF is sampling at more than 1 bit.
Of course.
Does that change the performance?
No.
Okay.
Because all of them is configurable, so you can change this through all of this. Like from the carrier mixer, and also using the lookup table. So it depends on how many bits you want, you can change it. And also this is the same thing here. Yeah, the problem here is that I think because this is a little bit different, so I'm not sure that we can use the hardware adder here or not. But the input bit here is very high. It depends how many taps you want to use.
Actually, I'm referring to the
I was thinking of the NCOs actually. So you store the values in the increment value and the accumulator are stored in your memory, and then you use the address to kind of cycle through each one. But you've still got to have an arithmetic operation from reading one memory and putting it into the next one.
Yeah, exactly.
And
that is much better than
and those would have the same width of your memory, which is like 32 bits.
Yeah, that's better than we use this here.
Yeah.
But in this case here, we develop this by ourselves, that we can control all of this through the chain and address here.
Yeah.
Yeah, in page 8, so this cost function plot, could you bit explain about how can we interpret this?
This one.
This is much more complicated. Go to the simpler one, page 8. Yeah, page 8. Yep, here. So how can we interpret this?
The thing here is that it's very difficult to compare all of these characters like directly. Yeah. So I have to normalize and separate this like in the range from 0 to 4. So after you count
each direction, that is the development cost direction.
So the smaller you want, the lower cost function you have.
Yeah. So no, I'm talking about those points there. How do you plot those points?
How do you evaluate them to become full? Like what criteria?
So not what criteria, but how do we interpret this? Because I can see that one particular line is reserved for one particular solution. So these lines are just going joined in what way? So that's what.
No, it's not joined here because there is just draw is like for each of them. Like for example, like for the GPU software receiver is the purple.
Yes.
So the resource is the highest one.
Yes.
The memory capacity requirement is the highest one. The power consumption and the I/O latency is the highest one.
Okay.
And the development cost is more because it's software. And the programmability is small too because you can reuse this.
Okay, now I understand. So basically, you pick a particular.
I pick a particular one of these architecture and draw one of them, and that does combine all together.
Okay. And in page 29.
And just while you're still on that, some of those things can be evaluated numerically, and some of them are just.
Yeah, some of them you can't.
Yeah.
Okay.
Are you the first one who came up with a photo picture like this? Are you the first one who came up with this way of evaluating? And do you have performance metric, like how do you calculate between 0 to 4?
I have some function to calculate it.
Yeah, so a performance metric that is mathematical.
Yep.
Okay.
And 29. Yep. 29. Yep. Why is this jumps happening in between? So we can see most of the points are going. It's not exponential, but going rapidly down. But there's sudden jumps in between.
The sudden jump here is that when the sampling is an integral term.
Yeah.
So when it's an integral term, you can see that you have the flat top. So because of this flat top, so the errors can come up like to one sample. So when it's the one sample, like 3 samples per chip, so it's this high.
Okay.
Just that, and also that x-axis is understandable.
Yeah.
Yes.
If you sample it more densely, each of those lines that goes up is very narrow. It's not a triangle like that. It's like there's a certain point where there's trouble, and then you move not very far away and there's not trouble. Like the 4092 and the 4093, right? So that's a little bit deceptive. And you didn't put the densely sampled one up in your presentation, so you didn't see that.
Yeah, exactly. Got this. Yeah, when it's too many things, I can't put everything here. So
Part of the reason that came up was Kevin's frequency plan that he uses for his GPS receiver is just that really bad one there, number 4. So we kind of saw it and we thought, oh, that's not good.
But it doesn't affect every satellite all the time,
That's right.
because you get both coded and Doppler, coded and carrier Doppler,
yeah.
which both help you.
Anyway,
Yeah, because the thing is only happen for Kevin because the sampling frequency is high, like 16 sample per core chip. So the Doppler sometimes can have this.
that's right.
But
And
if
then-
your sampling frequency is very low, like 4 sample, 2 sample per core
Yeah,
chip,
we
so
were
you can see it's
subsampling
like
that to
every
find
time
out.
it's happening.
to try to make it more efficient.
Yeah.
And of course, the downside of subsampling it is you get those errors get made even bigger than they were before.
Yeah.
So it sort of ties in with your power saving.
Yeah, because the thing is so happy because I just with the decimaler here. So I just try to downsample the signal, the baseband signal that I like 2 sample per core chip or maybe like 4 sample per core chip. So in this case, this always happen.
Yeah.
Yeah. So that is good that when we apply the solution, we can omit this.
So if you go back to the previous figure, just like this one, yeah, does the amplitude change when you have different bits per sample, number of bits per sample?
No, the amplitude
Does it change
doesn't
much?
change. That's what I figured.
Okay.
It's a timing thing, not a signal.
Did you look at that though? Did you look at bits per sample as an issue?
I haven't, but I don't think it is important.
Yeah, I can't see the mechanism where that would cause.
Will the bits per sample reduce the width of the 0?
No, this doesn't affect anything.
Theoretically,
Because the thing here that is all come back from the derive discriminator function. So the output of derive discriminator function.
What you might find is
yeah.
for like low numbers of bits per sample, because your C&O goes down, you lose, you go 1 you may actually find for low bits per sample that your remedies are actually better.
Yeah.
It may be, you know, the problem itself may not be changed, but the way the remedies work.
I think that
Actually here for this all of the result when I have here that when I have like 8 bit per second. The last one.
so if you go down to 1 bit per sample, I think
It's very
it will be
high.
more exaggerated.
Yeah.
Yeah. So
Yeah. Because all of the result I have here from the blade diagram is like 8 bit per second.
because we do know that the tracking error changes when you change
Yeah.
the sampling.
Just adds to your
To your future work.
future work. Just,
Yeah.
you just add that as a
Good research always has more future work, so that's good.
Yeah. Okay, anything else from anybody? All right, okay, so you young researchers who are still going, you can be inspired now by this brilliant piece of work from Vinh, all of his results there, lots of what I like about this, one thing I like about this work is how visual it is, you can actually see what's going on, which I think makes it easier to understand in many ways. Okay, that's enough listening to technical stuff, so it's cake in a day and a half, right? So let's get thanks, Vinh.
So it's nice to know.